The Birch-Swinnerton-Dyer conjecture, aka BSD, is a problem in mathematics so hard that the Clay Institute in Boston will give $1 million to anyone who proves it. BSD conjecture is a part of number theory, where solutions to equations are preferred to be found in rational numbers. In school, we have learned how to find rational solutions of one-variable equations of any degree n, and also of two-variable equations in degree 1. Now what about two variables in degree 2? Consider x squared plus y squared is equal to 1. This is known as a unit circle. -1, 0 lies on the circle. Take another point, P, x, y. The slope connecting these points is clearly rational. Using all the rational slopes and finding the second point of intersection, we are able to determine all the rational points. But x squared plus y squared is equal to 3 has no rational points. Summing up, we can have no rational solutions or infinite rational solutions. How about equations of two variables in degree 3? They can be written as y squared is equal to x cubed plus ax plus b and is known as an elliptic curve. We have no general method to find all the rational solutions in cubic equations of two variables. Let's compare it to the quadratic case and understand why. Unlike the quadratic case, cubic also has finite number of solutions and 3 points of intersection. In the cubic case, we need 2 rational points to find the third rational point.
This leads us to the crucial concept of rank of an elliptic curve. Rank of an elliptic curve tells us how many points we need to generate all the rational points on the curve. It is the key to determining all the rational solutions. In 1960, Birch and Swinnerton-Dyer decided to attack this problem by numerical experiments on a computer, by counting and not by algebra and geometry. They took many elliptic curves and counted the solutions for each and related it to the rank of the elliptic curve. But they had a problem: how to count large infinite solutions for many of these curves. The answer was modular arithmetic. Imagine a one-hand clock going from 0 to 4 and we have to count till 20. All the numbers can be counted in terms of 0 to 4. Since we have 5 numbers, it is modular 5 arithmetic. This way, an infinite set of counting is reduced to a finite set. Here's a question. How big is NP, the number of all rational solutions on an elliptic curve in modular arithmetic P? Well, it will have P minus 1 points in x and y respectively, which will give us P slopes and thus P points. Hence, NP should be close to P. Now we have all the tools necessary to understand the BSD conjecture. We take the product of NP upon P, where P is less than some large x for an elliptic curve. It should grow as log x to the power r times a constant. R is the rank. When r is equal to 0, it should have 0 or finite solutions, NP upon P is constant, and when r is greater than or equal to 1, it should have infinite or greater solutions, NP should be greater than P. Here's $1 million question, no pun intended. Can one of us prove the BSD conjecture? If not, remember that at times, the pursuit of knowledge can be more satisfying than knowledge itself.